Hi, and welcome to this section of the Matrix Algebra Tutor. And in this section, we're going to use our knowledge of inverses and inverse matrices, and we're going to use that to learn a different method to solve systems of equations. Matrices at this level are really mainly used for solving systems of equations, different ways to do it. One way is to do the row reduction that we talked about, the Gauss-Jordan and the Gaussian elimination. Here we're going to use inverses, okay? Now remember back when you learned how to solve regular old equation, just regular equation from Algebra 1, not even a system, just one equation. You had to learn very quickly that the opposite of multiplication was division, the opposite of addition was subtraction, the opposite of a square was a square root, etc. You had to know what the opposite operation was so that you could kind of use those in your equations to get the variable by itself and to solve it. So now that you know that the inverse of a matrix is sort of the opposite of a matrix, it's going to come as no surprise that the inverse matrix is going to be very useful for solving matrix equations. That's why we learned it. It's sort of an opposite. Okay, you're going to be able to use it just like you can use addition to cancel multiplication, to cancel subtraction, etc. Okay, so let's go ahead and just dive right on into a little practical example and let me show you how that's possible. So what if, let me ask you to consider the following simple system of equations. 3x plus 2y is equal to 7, and x, let's call it negative x, plus y is equal to 3. Okay? Now, that's nothing too special about that. It's two equations and two unknowns. Now, I'm going to show you that you can write this in matrix form. You can write this equation, and we already know that you can write it as an augmented matrix. You can write the coefficients here, and you can put a dotted line, and you can put the right-hand stuff over there. That's called an augmented matrix. But when you write an equation in matrix form, that looks like the following. You go ahead and write a separate matrix with the coefficients here, 3, 2, negative 1, 1. Close your matrix up, put another matrix here, put x and y inside here, one on top of another. I'll show you why we did that in just a second. And you set that equal to the numbers over here, 7 and 3. So you can see all the information is here. You have the coefficients here, and you have the stuff on the right-hand side of the equal sign. Why is this equivalent? Why is this, the matrix form, equivalent to what's on the top? Because when you think about it, if you were to take this matrix and actually multiply it by this, what would you do? You would go over and down, over and down. 3 times x gives you 3x, 2 plus y gives you 2y, equals the top number, which is 7. Okay? You would move to the next row. Negative 1 times x, negative x, plus 1 times y gives you the y, equals what's on the right-hand side. So it's truly a matrix representation of this system of equations. Coefficient matrix times the variable matrix, they're always written on top of one another like this, is equal to what's on the right-hand side. And this is a compact way of writing this whole system, because if you do the matrix multiplication, you exactly come back with the equations that you started with. Okay? So why am I doing this? Because what you need to remember, and what you need to learn, okay, this matrix that has the coefficients of everything is called, in general, the matrix A. Okay? I'm going to put little quotes around it. This matrix that has the actual variables that you're trying to solve for is called big X. Okay? We'll talk about that in a minute. This matrix that's on the right-hand side of the equal sign is called B. So what you have is A times X is equal to B. Matrix A times matrix X is equal to matrix B. That's the matrix representation of this. Matrix A times matrix X is equal to B. This is called the matrix form, the more compact way of saying